Hello and welcome to this EEE 141 lecture on pole movement and gain bandwidth trade-off in feedback amplifiers. Our objectives for this lecture are the following. First, to relate the open loop frequency response of an amplifier to its closed loop frequency response when in feedback. Specifically, we will identify how the poles and zeros from the open loop move, if indeed they move, when in feedback. Next, to explain the trade-off between gain and bandwidth when using feedback. And lastly, to demonstrate a circuit-level frequency response analysis example of a simple transistor feedback amplifier. Shown here is the same block diagram we have been using to analyze signal flow in negative feedback. However, there is one major change. Instead of writing the forward gain as A, we are now writing it as A of S. And thus, we are now considering a frequency-dependent forward gain, now possibly with some zeros and/or poles. However, the feedback block still maintains a feedback factor of F without the S, and thus we are considering only or limiting our analysis to frequency-independent F values. This is true for feedback networks made of purely resistive devices. Of course, there are cases where the feedback network may contain reactive components or even amplifiers. However, limiting the analysis to purely real, frequency-independent F can still help us uncover interesting properties of feedback in the frequency domain. Since the loop gain is simply the product of the forward gain and the feedback factor, then the loop gain essentially becomes frequency-dependent as well. Now, if we look at the feedback system as a whole, and closed-loop transfer function ACL of S, will it have the same poles and zeros as the forward gain? The key to answering this question is by inspecting how the frequency-dependent terms appear in the closed-loop response. We will go back to the same expressions for the closed-loop gain, although this time A and T are both frequency-dependent. To move forward systematically, we will consider a generic response for the forward gain in the form shown. Note that the pole and zero terms are written as 1 plus S over P and 1 plus S over Z respectively, instead of S plus P or S plus Z. The format shown is preferred so that the factor outside will be the DC gain, which is the one left when the expression is evaluated with S is equal to 0. We will use the terms forward gain and open loop gain interchangeably in this lecture and the following lectures. These terms should also always, in our context, refer to the loaded open loop gain. From the forward gain, then the loop gain can be written T of S. Since the feedback factor F is just some constant, then the loop gain will have the same poles and zeros as the forward gain. As a shortcut, we can write A of S and T of S as shown, where N of S is the numerator composed of the zeros, while D of S is the denominator composed of the poles. While A of S and T of S has the same zeros and poles, the case for the closed-loop response is different. Starting from the generic expressions previously shown, if we expand T of S into T naught N of S over D of S, and then factoring out the constants so that we can isolate the DC closed loop gain, it can be shown that the closed loop response is ACL naught 1 plus T naught N of S all over D of S plus T naught N of S. The zeros are determined by the numerator. Since 1 plus T naught is just some constant factor, the numerator will only be 0 when N of S is 0. Thus, the closed loop gain has the same zeros as the loop gain and the forward gain. Meanwhile, the poles are determined by the denominator, and if we equate the denominator to 0 and then divide by D of S, it can be shown that the denominator of the closed loop gain will be 0 when 1 plus T of S is equal to 0. Thus, the closed loop gain has different poles than the loop gain and the forward gain, and we need to inspect further when 1 plus T of S is equal to 0. Consider a common or rather ideal case where the forward gain only has a single pole. Again, assuming that f is purely real, then A and T will have the same exact poles but different gains. What then is the closed loop response? Written here is the form of the closed loop response from the previous slide in terms of N of S and D of S. Now we know that for the case we're considering a single pole forward gain, N of S is simply 1. So we can substitute N of S into 1. And then replace D of S with 1 plus S over P1. And so we get this expression right here. Now, if we focus on the term on the right only for the meantime, we can rearrange the terms such that we put the terms without S on the left side of the equation and put the term with S on the right side of the equation at the denominator. Now we can factor out 1 plus T naught. So we multiply 1 plus T naught here and 1 plus T naught here. And then factor out 1 plus T naught at the numerator. And so we get this expression right here. And after doing so, we can cancel out 1 plus T naught. And so this term here is simply this term here. And therefore, the closed loop response can be written as sum A naught over 1 plus T naught, which is the DC closed loop gain, times 1 over 1 plus S over P1 times 1 plus T naught. Thus, the forward gain or open loop gain without feedback has a DC gain of A naught and a pole at negative P1, which is shown on the pole 0 plot on the right at negative P1. When used in feedback, the closed loop gain becomes A naught over 1 plus T naught, and the pole now is at negative P1 times 1 plus T naught. One critical observation is that the DC gain or in-band gain decreased by a factor of 1 plus T naught, but the bandwidth, as dictated by the first pole, increased by the same factor 1 plus T naught. Thus, the pole moves towards negative infinity of the real axis as T naught is increased for our single pole case. Note that when T naught is 0, or when there is no feedback yet, then 1 plus T naught is simply 1 plus 0 or 1, then we end up with the open loop gain pole location. Now let's look at some numerical example. Consider a system with a DC forward gain of 10,000 and a feedback factor of 0.1, which gives a DC loop gain T naught of 1,000. Say the pole of the open loop gain is at 100 radians per second as depicted on the plot. If we consider only DC, we should be able to compute that the DC gain or DC closed loop gain is A naught over 1 plus T naught, which is 10,000 over 1001, which is approximately 10, which is 20 dB. Using our observations from the previous slide, the pole of the closed loop response must be at the original omega P1, but now multiplied by 1 plus T naught, or 100 times 1001, which is approximately 100 kiloradians per second. This is also shown in the gain plot, where the closed loop gain starts decreasing at around 100 kiloradians per second. Thus, with feedback, the single pole system's gain decreased from 10,000 to 10, as shown here, from 80 dB to 20 dB, while the bandwidth increased from 100 to 100 kiloradians per second from this point here to this point here. Now let's look at what happens when we originally have two poles instead for our forward gain. The forward gain can be written in the form A0 over 1 plus S over P1 times 1 plus S over P2. Note that we are considering poles in the left half plane of the S domain. We will skip the step-by-step derivation of the equations, but the closed loop gain can be written in the form shown after making sure that the DC closed loop gain is in its familiar form and factored out on the left side. We now focus on the denominator and check at what S value or S values thus the denominator become 0. Before proceeding, it must be remembered that minus P1 and minus P2 are the poles of the forward gain and of the loop gain, but not of the closed loop gain. The roots of the denominator are the locations of the poles and of the poles of the closed loop response. From how the expression was written, it must be noted that T0 only affects C and the determinant. As T0 and thus as C is increased, the term inside the square root will become smaller and approach 0, where the two roots now will overlap. As T0 is increased beyond this, the determinant will be negative, and the roots and thus the poles will become a complex conjugate pair. Note, however, that since minus b over 2a does not change, only the imaginary part will change once the roots become complex conjugate pairs. If we look back at the expression, the gain still decreased by a factor of 1 plus T0. However, it can be shown that if the poles are still at the real axis and far enough from each other, then the bandwidth is still decreased by 1 plus T0. Now we will prove that statement or claim that the gain bandwidth trade-off still exists for our two-pole system. We know that with feedback, the closed loop system will still have two poles, and thus the denominator of the closed loop response can be written in this form in terms of P1CL and P2CL, regardless if these poles are far from each other, overlapping, or even complex conjugate poles. We can then multiply the two terms and get this expression or form right here. Now, from the original expression in terms of the open loop poles and the loop gain, although this time we divided it by 1 plus T0, the denominator can be written in this form. And we can therefore conclude that these two expressions right here must be exactly equal. And then note that by dividing this term right here, or this form right here, by 1 plus t naught, the 1 at the end of the equations now match. We will now invoke a special condition, as mentioned a while ago, that the closed loop poles are widely spaced apart in the real axis. And if this is the case, then the original poles must be widely spread as well. And so in equation wise, we have here P2Cl is much greater than P1Cl, and therefore P2 is much greater than P1. So these are the open loop poles. Now, if that is the case we are considering, then P2 is much greater than P1 for both cases. Then the terms at the middle, the one with S, can be simplified. So 1 over P1Cl plus 1 over P2Cl can be simplified as 1 over P1Cl, since P2Cl is very large compared to P1Cl. And the same is true for this term here. We can approximate it simply to be 1 over P1. We can then compare the two equations with the form shown. It can be easily seen that the first pole of the closed loop gain, or closed loop response, which dictates its bandwidth, occurs at P1 times 1 plus T naught. And so the same gain bandwidth trade-off is seen in a two-pole system as long as the closed loop poles are still real and widely spaced apart. Additionally, if we approximated the first pole of the closed loop to be P1 times 1 plus T naught, then for the S squared term, we know that we already have an approximate expression for P1Cl, which is P1 times 1 plus T naught. Then it can be shown that with our approximation here, the second pole of the closed loop is now approximately equal to the second pole of the open loop. Let's now look at some circuit level examples and check if the same concepts indeed come up when using feedback. So use feedback analysis to derive the transfer function VO over VI of S for the shunt-shunt feedback amplifier shown, disregarding parasitic capacitances. Note that a shunt-shunt amplifier samples the output voltage and feeds it to a feedback element, and then subtracts some feedback current from entering the forward amplifier, which in this case is a single transistor amplifier, a common emitter amplifier. In the schematic shown below, the hybrid pi model of the transistor is used. So we have here R pi, GMVBE, and R naught, with the load resistance RC and load capacitance CL appearing at its output and then connected to AC ground. The feedback element RF is connected from the output node, the collector, back to the base of the transistor. The feedback element samples Vout and subtracts some IFB at the input side. The input also shows the input voltage Vi and the source resistance Rs. The input is source transformed to highlight the current subtraction that happens at the input of the transistor amplifier. The current input I sub I is now Vi over Rs. The feedback element's unilateral two-port model is also shown. Its input and output resistances are both Rf, and we modeled the transfer from the output signal to the input signal as some transconductance, knowing that this block's input is some voltage and its output is some current, and the transconductance is some -1 over Rf, and so the voltage dependent current source's value is V out, negative V out over Rf. We can then further simplify the circuit by combining Rs, Rpi, and Rf into some single R1, R0, Rc, and Rf as some single resistor R2. And we also know that the error current IE is II minus IFB, and that the input to the base of the transistor is some error voltage VE, which is IE times R1. Since we have already lumped all the resistors at the input and at the output side, it is now easy to determine or set up an equation for the output voltage. As indicated, V out is simply minus GM VE, which is the current here, times the impedance at this node, which is R2 parallel with 1 over SCL. Note that this side now is already open, so the current will just flow through these two components here. We then substitute VE, this VE here with IER1, and expand the impedance at the output side. So R2 parallel 1 over SCL is R2 over SCL all over R2 plus 1 over SCL. Now, to get the forward gain from the error signal to the output signal, we have to isolate V out over IE on the left side. Now, the right side is now minus GM R1 R2 over 1 plus S over 1 plus S all over 1 over R2 CL. And we can denote this term here under S as some P1 for the pole of the forward gain. Thus, for the forward gain, the pole is 1 over R2 CL, and its DC, the DC open loop gain is minus GM R1 R2, and therefore we can write this V out over IE as our A of S for this circuit. Again, note that the forward gain for a shunt amplifier is V out over IE and not V out over VI nor V out over VE. The DC open loop gain is also has this negative sign, meaning it is inverting. Now the feedback factor, which is IFB over V out, is simply -1 over RF, which can be determined simply by inspection. And note again that its value is also negative, or we have an inverting feedback factor. Multiplying the two expressions, A of S and F, we get the loop gain T of S. And so we just multiply these two terms here, and the DC loop gain is now positive, GMR1R2 over RF, and the pole is still P1, which is 1 over R2 CL. It should also be noted that the loop gain must be unitless. So that is one thing that can be used to double check your expression, since the loop gain is feedback signal over error signal, which should always be of the same form, current or voltage, regardless if the system is, or the feedback is shunt series, series shunt, or series. We can then write the closed loop gain based on the forward gain, the feedback factor, and the loop gain. The closed loop gain for the shunt system is V out over II, and one of the known forms of the closed loop gain is 1 over F times T of S over 1 plus T of S. Then 1 over F is simply negative RF, while T of S is this expression right here, which is substituted in this equation or form. We can then multiply both numerator and denominator by 1 plus SR2CL, and so that would cancel out with this one, and so we're left with GMR1R2 over RF, and this one simply becomes 1 plus SR2CL, and we have this GMR1R2 over RF. We can then factor out this 1 plus GMR1R2 over RF, so that the denominator can be written in the form 1 plus S over something, which is the one shown here. So we factor out 1 plus GMR1R2, we just move this term right here to this side, and so we're left with 1. The term without S is factored out, so we're just left with 1, and therefore we have to divide that term to this SR2CL. So we have this SR2CL over 1 plus GMR1R2 over RF. And doing so, we note that we are already able to write the closed loop gain in this form A naught over 1 plus T naught, which is the DC closed loop gain, over some 1 over 1 plus S over P. Although this time, the pole from the open loop is multiplied by 1 plus T naught, or 1 plus GM R1 R2 over RF. Note also that the denominator or sorry, the DC closed loop gain now follows this term A naught, where A naught is minus GM R1 R2, which is also shown here, minus GM R1 R2, and the RFs will just cancel out, and the denominator is 1 plus T naught. So again, 1 plus GM R1 R2 over RF. And that should be our closed loop gain for our shunt amplifier. However, that closed loop expression is actually V out over II, consistent with the standard variables for a shunt amplifier. If we want to get the gain based on the originally defined VI, then we simply reverse the source transformation, where II is VI over RS. And so isolating V out over VI, we can see that the closed loop gain we have derived is actually equal to V out over VI times RS. Thus, we just need to divide the closed loop expression we have derived by RS to get V out over VI of S. Doing so will give us the expression shown with the additional RS at the denominator. Now, it must not be forgotten before making any approximation or assumption with this expression that both R1 and R2, which appears on the gain and on the bandwidth or the pole, are both dependent on RF. Now, if the DC loop gain T naught is much greater than 1, meaning GM R1 R2 over RF is much greater than 1, or that GM R1 R2 is much greater than RF, then the DC gain from VI to V out is simply minus 1 or negative RF over RS. So again, if T naught is very large, then the DC closed loop gain is simply negative RF over RS, which is the same form we get for an inverting op-amp configuration with the same connection for RS and RF. A notable difference is that the transistor accepts the input at the base, but the common source amplifier has an inverting gain. Meanwhile, in the op-amp circuit, the op-amp itself is non-inverting, but the input is connected at its inverting terminal. So we were able to show that these two circuits will end up having approximately the same DC voltage gain. Now let's look at a real op-amp example and check what the gain bandwidth trade-off, or what gain bandwidth trade-off we are really dealing with, specifically with an LF353 op-amp, which is marketed as a wide bandwidth high-speed op-amp. From the datasheet, the typical gain is around 100 volts per millivolt of input, or 100,000 volts per volts, or around 100 dB. The datasheet also indicates that the gain bandwidth product is 3 megahertz. So what then is the typical bandwidth for this part? We can thus solve by dividing the gain bandwidth product by the gain, and thus 3 megahertz divided by 100,000 will give us only 30 hertz, although the op-amp is already considered wide bandwidth. Now this value is also close to the value that can be inferred from their sample gain plot from the same datasheet. So aside from the bandwidth, this also shows the gain of around 100,000 and the gain bandwidth of around 3 megahertz. And we can also see that they have designed their op-amp to have a single pole response. Thus, the wide bandwidth they are referring to is actually the gain bandwidth product. And we know that the high gain of the op-amp can later on be traded off for bandwidth. Okay, and although this open loop gain is not perfectly controlled or accurate, the closed loop gain can be designed to be smaller, possibly from ratio of resistors used with the op-amp. However, that closed loop gain will be more accurate, since the closed loop gain is dependent approximately on 1 over f, requiring only that the open loop gain is very large but not necessarily accurate. Thus, also given two op-amps configured for the same closed loop gain, the one with the higher gain bandwidth will achieve the larger closed loop bandwidth, although that statement will only be always true if the loop gain exhibits a single pole response, or at least a single pole until the unity gain frequency. Although we'll learn more, or that statement will be clearer as we learn more about feedback frequency response in the following set of lectures. Okay, so in summary, with negative feedback, the pole locations of the forward gain will move depending on the amount of loop gain. For a single pole system, the left half plane pole will move away from the origin towards negative infinity of the real axis. For a two-pole system, the poles in the real axis will move towards each other as the loop gain increases and can eventually become complex conjugate poles. Negative feedback moves the first pole away from the origin, and thus the bandwidth increases by a factor of 1 plus T0, while the gain decreases by a factor of 1 plus T0. Lastly, the high gain of an op-amp can be traded off for additional closed loop bandwidth. However, this is limited by the gain bandwidth product of the op-amp. And that's it for this lecture. In the next lecture, we will see how we can plot the frequency response of feedback amplifiers and also introduce stability issues that can be encountered when dealing with feedback. Thank you for listening, and I hope you learned with this lecture.